Yeah, the talk of today is about going from 2D to 3D. So 2D data is something that we are more or less used to, but 3D data way less. And in our lab, CVLab, which is right at the floor below here, we work mostly on 3D data. So the problem is, how do we represent 3D stuff? And how do we go from our 2D data, like images, to having something in 3D? So this is the general pipeline that we want to talk about. And we'll try to, divide it in the multiple steps that are involved. And then we will also talk about some of the applications of 3D stuff. So this is us. Federico is me, Sakib is here, and Chen is online. I'm going to talk about coordinate networks and how to represent the shapes. Sakib is going to talk about scene reconstruction, mostly using Gaussian splatting. And Chen is going to talk about pose estimation. So just a couple of words about me. I'm Italian. I moved here from Rimini. I graduated in Italy, in Bologna, both bachelor's and master's in computer engineering. And now I'm here in my fourth year doing PhD. And yeah, I mean, I was briefly a high school teacher, and I had another brief experience in a tech startup that didn't go very well. So then I started my PhD. But teaching was always nice. So that's also why I continued in academia. And I'll also start an internship in Meta next month. So I'm very excited about it. But that also means I won't be here for a few months. So I'm going to propose a bunch of projects, but it also means that I cannot directly supervise them from here. I'm going to be able to supervise them, but I'm going to be, of course, remote. Okay, so let's start. What are coordinate networks? That is the first question. So you know what a neural network is, I guess. Who knows? All of you, more or less? Okay, good. So in a neural network, you of course have a bunch of inputs and a bunch of outputs, one or more. And they usually are trained with some training set, and you usually want them to be able to generalize to some test set that is related to your application. What we mean by coordinate networks is simply networks that have as input coordinates, okay? Spatial coordinates. They can be x, y, for example, in a plane, x, y, z in space, or more. Okay, sometimes you have more coordinates than this. And this basically means going a bit more to the basics of what a neural network is. You might have heard the theorem that says that the neural network is a universal function approximator up to some extent. Okay, so a neural network defined in a specific way, constructed in a specific way, can approximate to some extent any function. And this is how we use it, as a function approximator. Okay, so we have a function that takes coordinates, and we want this to output something. And this is just a function. We use the neural network as an approximator for that function. So there's no specific training set or test set in this scenario. Okay. What do we output? Well, it depends on what we want to do. There are implicit surface representations, which is what my research is mainly about. There is NERF. You've heard about NERF, I guess. Some of you have. Yeah. And then there's many other things. You can do image compression and other stuff, but I will not talk about this. So let's start with the implicit surface representations. So there's many ways to represent surface, and there's many things you can do with surfaces. So for example, you might want to do shape reconstruction. You might have a bunch of noisy inputs from, let's say, a depth sensor. You might have, they might be noisy, they might be partial, so occluded in some parts. You might have only one side of an object, not the other side. You might want to do shape optimization. You have some specific parameters that you want a shape to optimize for, and you want to do that. You might want to do classification, segmentation, rendering, and a bunch of other stuff. How do you represent a shape? So in general, when you represent a shape, you want to encode as much information as possible in as little space as possible, of course. You ideally don't want to be limited in resolution, and you want the representation to be easy to process. In the field of 2D, this is very easy. You have images, okay? Of course, you can have different compression techniques, different formats, but we all agree that an image is just a matrix of pixels, okay? So it's an easy representation. There are CNNs, there are transformers that can work with that. In 3D, it's not the same, okay? There's many ways to represent the surface, and they all have their own advantages and disadvantages. In a voxel-based representation, the main advantage is that it's very straightforward. You have an image, it's a bunch of pixels in 2D, just generalize it to 3D, you have voxels, okay? This is just the same thing, it's just as an image, but in 3D. So you have voxels in 3D. It's very easy to work with. You can just take a CNN that you define for 2D, You add an axis, you have a 3D CNN, and that's it. Okay, very easy. The problem is that it has a huge memory footprint, and it's difficult to process in the sense that as soon as you go high resolution, let's say 128 or 256 to the power of 3, you get a huge size very fast, which means not only it's problematic in memory, it's also problematic in time, the time you need to process it. So it's, it's possible. People have used that, especially in the past. It has enabled something, but it has many limitations, as you can see. Another representation is point clouds. So in a point cloud, you have a bunch of points. Each point has a precise location in space, and you only save that location. So there isn't that much information to save. I mean, unless you have like billions of points. So you have a fairly lightweight representation. It's easy to obtain because that's what you get from a 3D scanner, from a LiDAR, from a self-driving car. You have a bunch of points in space. So you have a point cloud. They're a bit harder to process, but there have been neural networks that are able to process it, like PointNet and PointNet++, and others as well. But we can kind of see a bunny there, but there isn't really a bunny shape. There's just points. There's no connectivity between points. We see it as a bunny, but there is no real surface in this. So since it's lacking connectivity information, it's not really having everything we need, to define a surface. Then there are meshes. Okay, this is probably the most important representation for shapes. In a mesh, which is what you use like for, represent assets in video games or for rendering or basically any 3D task, you have a bunch of points in space, but you also have edges between them. So all the connectivity information is there now, okay? Which also means that you need way less points to encode a shape because you have all the connectivity information between them. So it's nice, it's lightweight, it's fairly easy to process. You need specialized network like graph neural networks that are able to work on graphs. You can see a mesh as a graph because you have nodes and edges between them. But it's not so straightforward to process because, again, you need a specialized network, and it's if you want to do some of the tasks that are specified, like optimizing a shape to do something specific, you might want to modify the shape. But how do you modify a mesh? You can, for example, inflate the bunny or shrink the bunny, but to modify the shape more, you would need to remove some edges or add some edges, remove some points, add some points. And that's something that is usually difficult to do. Changing the topology of a mesh is usually something difficult to do. You can do it by hand, of course, but having something automatic that handles all of this is usually problematic. So there has been yet another representation, which is called implicit representation. And there's two main ways to do this. One is occupancy field, and the other is sign distance field. Let's just focus on sign distance fields for now. In a sign distance field, you basically define a field in space. So for each point in space, you define the field as the distance from that point to the closest surface with a sign. The sign is positive if you are outside of the surface and negative if you are inside. Okay, so here you see a 2D slice of a bunny. You have all those SDF points in red that are out of the bunny, so they have a positive sign, and inside they have a negative sign. So this is implicit because we define a field. Okay, the surface is implicit in the field, is a zero-level set of the field. But it still defines a surface. And this has nothing to do with neural networks yet. This is just a way to represent a surface. But as I told you, a neural network is a general function approximator, so we can use the neural network to approximate the field. So we can parameterize the field with a neural network, which then becomes the shape itself. So the neural network encodes the field, which encodes the shape. So the neural network becomes the shape. If now you train this neural network to approximate this field, you can save the weights of the neural network in your storage, and those weights represent the shape in a very implicit way, but they represent the shape. So what advantages do we have here? First of all, it's continuous. We don't have a specific resolution limit, okay? Of course, we have a representation power limit of the network. The bigger the network, usually, the more representation power it has, but we don't have a specific resolution limit. It usually has a very limited memory footprint. It's usually lighter than the mesh, especially if you encode multiple meshes with a single network that I'm going to show in the next slide. you can represent fairly detailed models. And with this, you can change topology. Okay, this is very important. The fact that you can change topology freely. And again, I will show examples of this. Yes.
Functions that don't correspond to any reasonable field, like can you write a function and call it an SDF, but it's not renderable? It doesn't make sense.
To be an SDF, you need the gradient of the field to have norm 1.
I don't know what that means, whether there's a simple question that says this is a sense of this.
Yes, yeah. Since it's a sign distance function, if you go closer to the surface by 1 step, then your field has to be lower by 1. That's what it means, to have a gradient of norm 1. So that's what you need.
Yeah. Thanks.
Yeah.
Sorry. So, in general, how do you collect the data? Because you need the data.
Because yeah, that's a good point. So in general, when you start this, you already have the meshes. Okay, this is just about the representation of the surface. We're not yet going from 2D to 3D, but just for the representation of the surface, you do start by having some surface. So let's say you have the bunny. You need the bunny, the mesh of the bunny, to be able to compute a ground truth SDF that you use to train the network that then approximates the SDF. This doesn't do anything yet. It doesn't serve any purpose, but it will serve a purpose in the next slide. And also, if you have any questions, feel free to stop me. I forgot to say it at the beginning of so how do we present multiple shapes? Because this is what really useful. It's useful because maybe we can compress them more. And yes, we can. And it's useful because maybe with a single network, we are then able to optimize the kind of shape that we want. Because then a single network represents a range of shapes, and then we can find the shape that we need for our task. So this is the useful part. So you've seen the autoencoder, I guess. This should be probably familiar to most of you. In an autoencoder, you have an input that gets compressed to a latent code, which then gets decoded to the output, which should be as close as possible to the input. Okay. What is used for these implicit representations is an autodecoder formulation, which is similar, but it's missing the encoder completely. So you have the latent code, you have the XYZ coordinates in space, which you need because it's a coordinate network, and it outputs the SDF. So the latent code represents the shape. Okay, so for a specific latent code, you have a specific field, which will encode a specific shape. If you change the latent code, you will get a different shape. So what you typically do is that you train an autodecoder to learn, let's say, a set of cars, of many different kinds of cars. Each is going to have a different latent code. And then in practice, you may want to optimize the car shape, let's say, to reduce the drag. Okay, so you optimize the latent code. You change the latent code until you find the one with the least drag. Okay, this is the general idea. Exactly. Yes.
Yeah, when you say XYZ, just to make sure that I'm on the right page.
Yeah.
It's not meant to be some representation that is understandable to us, right? It's not literally coordinates.
It's literally XYZ coordinates.
It is coordinates.
Yes.
Okay, it's not.
Yes.
It's not some network decided to represent.
No, literally coordinates. Yeah.
So you're basically mixing the latent representation with raw data, right?
With raw data, what do you mean? Sorry.
Is this also encoded, or is it raw data?
It's just XYZ. So remove the latent code. Okay, just imagine it's not there. You just have a coordinate network that given XYZ coordinates gives you the SDF in that point.
But let's say this is raw data. This is no encoding, whereas the code it is encoding, correct?
I'm not sure I understand the question. Sorry.
Normally, this part in blue.
Yes.
Is encoding, correct? Embedding.
It's an embedding, yes.
Yes, whereas the part in gray, it's raw data like XYZ coordinates.
Yes.
So we are mixing this raw data.
Yes. Sorry. Yeah.
Okay, so the output isn't SDF. The output is the SDF
in XYZ.
Point,
yes. I will be more mathematically correct next time. I'm kidding. No, you're right. You're totally right. Yeah. It's the SDF at that specific point. Yes. Okay, there's a problem though. So we have an implicit representation. How do we use it? Like we need something like a mesh to render it. We need something like a mesh to classify it. We need something like a mesh to do other stuff. So cool, we can change topology, we can optimize it, we can do all sorts of stuff, but we need a way to get the mesh out of it at some point. And to do this, we can use isosurface extraction algorithms like marching cubes and others. There's a lot of them. And this is actually an active research field, even nowadays. Marching cubes, the first three basically are from I don't know, like 30 years ago. The others are from last year and 2 years ago. It's still ongoing. The way you do it is, one of the ways you can do it is that you can query a 3D grid of points, and then you can compare the values in a single cell of the grid to check if you have both positive and negative values. If that's the case, there must be a surface somewhere there. Okay. So like, yeah, I mean, here it's not so easy to see, but I should have, yeah, something here. So in the case of marching cubes, what you have is that here, of course, it's in 2D, but it's the same in 3D. You have these grid points. Can't see my pointer. Okay, so in this case, this is positive, this is negative, this is positive, this is negative, this is positive, this is negative, and this is positive, and this is negative. Okay, so wherever you have a sign flip in an edge, it means that there must be a surface in that edge. Okay, so you can linearly interpolate the SDF values along that edge to find the zero. Of course, it's an approximation, but it's usually fairly accurate. And then the way you connect the edges, well, here is very simple. In 2D in general, it's quite simple. That's a lookup table that tells you how to connect. In 3D, it's way more complex, but it's still possible. So that's how you do it for marching cubes. There's another way, dual contouring, which is similar, but uses optimizes this equation to make it basically better for sharp details, but it's also a bit slower, so people still use both. This is the 3D lookup table for marching cubes. It's way more complex. Each of these cases has a bunch of subcases. And there's a guy in the 80s that implemented all of them, so we didn't have to worry about it. It just works. So this is like a recap of these representations. You have like voxels, which is just pixels in an image. You have points. You have a mesh, which, I mean, in this case, it's extracted with a specific method, AtlasNet, and you have the implicit representation. So what can we do with it? So this is an example. In general, what you need in this case is a end-to-end differentiable pipeline if you want to optimize something. So in this case, we start with a code. Deep SDF code is just that latent code that I showed in the autodecoder earlier. Use marching cubes to compute the mesh out of it. And then you compute whatever you need on this mesh in a differentiable way. And then you backpropagate everything, all the gradients, to the latent code so that you can optimize the latent code for something that you need. Okay. So in this case, what we need is a change in topology. Okay. So here we have no holes. We now want to have a mesh that has a hole in the middle. Okay. So we can define a loss for that and backpropagate that those gradients from that loss to the latent code. Okay. So this is what we would get. You go from one to the other. Yeah. Of course, this is still useless. What else can we do? We can go, for example, from an image. In this case, it's just a silhouette. Silhouette is basically a binary image. It tells us where the object is, to a shape. Okay. So as you can see, these are slightly different slides. I don't know if you followed the computer vision course by Pascal Foy. This is from that course. He's our supervisor. And in case you didn't, you should follow the course because it's very nice. Anyway, so you can go from an image to a shape. In this case, you can define the pipeline this way. So you have the autodecoder, you extract the mesh, you can then render the mesh in an image, and then you can binarize that image to have the silhouette. Then you can take that silhouette, compute a loss between that silhouette and the silhouette that you actually have, that you want to get a shape for, in a differentiable way, get back the gradients, propagate them to the latent code, optimize the latent code to get something that is as close as possible to that. Yes?
Since an implicit representation doesn't have like orientation object.
That's true.
Do we compare like one orientation of object to the other's orientation? Because like if we compare one orientation of one object to another orientation of the same shape, we still.
Yes, that's absolutely true. And this is more on the pose estimation side. So I guess Chen will talk about it. But in general, you need then more parameters. You need something extra, not just the XYZ and the latent code. You also need the pose information, like where are you looking this from? Which of course adds complexity. I don't remember if in this example there was pose involved or not. By the look of it, I would say no. But nowadays you can totally do that with pose as well, with different poses as well. Yeah.
You said a few times that you need to be able to compute all this stuff in a differential way.
Yes.
And I understand why that is the case. What I'm curious about is, do these functions tend to be naturally mostly differentiable, or is that like most of the secret sauce expressing these things in a differential way?
Sometimes it's one way, sometimes it's the other. In some cases, it's easy. For example, differentiable rendering is fairly easy nowadays. But differentiable drag computation is not easy. This is an ongoing area of research. So it depends. Sometimes that's the secret sauce. Sometimes it's just okay. You can get it for free, basically. Yeah.
I was wondering how robust the implicit representation is. Like, for example, if you mess up surface, like you have like plus minus plus, like if you compute with like the example with the issue, then you have a transit. Does that mess up with like the graded computations that you want, and like how generally how robust?
So here you mean if they're completely flipped?
Yeah. So like, is it possible to like use this? I think going back to your earlier question, like mess out the surface entirely in one specific area.
Uh-huh.
There was like some error, like any error.
Yeah.
Okay, so is it possible? Like how robust is it to errors?
So in general, SDF is very robust to errors, especially because usually when you train the network, you add a loss that ensures, softly of course, that the gradient is always of norm 1, which makes it like way more regularized. And in general, you don't have these like problems. You don't have like inversions or self-intersections or stuff like that. I think I've never seen it happen in practice. You can have, of course, imprecisions. Sometimes, you know, that the vertex can be shifted a bit up or down or left or right, but no big things usually. You can also extract a model from a sketch. It's similar. You get, you know, the model, you render it, you get the outline, and you compare it to the sketch until it's as similar as possible. Another thing you can do, as I mentioned, is drag computation. So you have the autodecoder, you get the surface, you compute the drag, and then you propagate, which means you're going to get, you know, the fastest car possible on a straight line. And this is possible only if you have a differentiable drag computator, which, you know, if you really want to compute the drag of shape, it's not differentiable. There's no way. But you can use surrogate models that approximate the drag of a shape. And the better the approximate model, the better this is going to work. And for example, you can go from, you know, a general car, in this case, an SUV. If you optimize it for drag, then you're going to get a sports car, to the surprise of no one. And this is has been used in practice to set 2 world records on human-powered bikes. And I mean, they don't really look like bikes, but they are bikes. There's pedals inside. And they use this exact concept. Okay. Any questions on SDFs? Yes.
Yeah. So what happens if we linearly interpolate from one embedding to another?
Yeah.
What happens with the shape?
You do get something in between. Yeah. Yes, you do. Yeah, yeah. Then, of course, now I simplified a bit. I just said you use a neural network to represent the decoder, but of course, different networks are going to behave in different ways. Sometimes it's smoother, sometimes it's less, and of course, you want it as smooth as possible.
Yeah, but
in general, yes. Yeah. So this is all very cool, but it's limited to one particular set of surfaces, which is watertight surfaces, because you need an inside. Otherwise, you can't do this. And this is what I mainly work on. So how to make this work on open surfaces. Let's say you have garments that don't really have like an inside or an outside. Or you have like data sets like this one, a ShapeNet for cars, in which, yes, maybe theoretically you can define an inside or an outside, but these are not really watertight in the way this data set was made. So you need a more general way to process them if you want to use them. And unsigned distance fields have been proposed to do this. So it's just the same as the SDF, but without the sign. Okay, for any point in space, you get the distance to the surface. There's a problem though. Like while an SDF was going, you know, from here, you know, from negative to positive, and it's differentiable everywhere, a UDF isn't. Okay, you have a singularity there. And there's others too, but that's the problematic one. So right on the surface, you have a singularity, which makes it hard to learn for a neural network and hard to mesh, so to extract the surface. Yeah, 1, 2, and 3. So all these are areas of research, current areas of research, and in the lab we're working on all of them. So if you're interested, of course, we can talk about it. I work mainly currently on the extraction of the zero-level surface. So let's talk a bit about it. So this is a work from 2022 of our lab. So let's say you have a UDF, and let's say you can compute the gradients of it. And the way you can compute the gradients of it is that you can differentiate the output, so the UDF, with respect to the coordinates. Okay. In this case, you get the literal gradient of the field. The gradient is going to always point away from the surface. Okay, but norm 1, hopefully, which means that if you look at the UDF values, it's hard to say where the surface is. But if you look at the gradients, it's a bit easier to say it, okay? In this case, they're all pointing away from the surface, so it's not hard to imagine that there should be a surface in between, okay? So in this case, what we do is that we compute dot products between the gradients to find like basically concordance and discordance between different gradients. And this brings us back to the marching cubes case, okay? We have these plus and minuses, which are not real plus and minuses, they're just local. But this means that locally we can apply the marching cubes huge lookup table to get a surface in that cell. Okay, so if you do this on a UDF, you get something cool. But if you do this on a neural UDF, which is noisy, only approximated, it's not real, it's not as simple as this. So you get a ton of problems. In this case, you get a lot of holes and a lot of self-intersections, for example. There's in general problems in this setting. In this case, we particularly wanted to mesh garments. Okay, we needed to represent garments to basically fit them on avatars. So what we can do here to solve this problem, at least partially, is to look at the neighboring vertices. Okay, if instead of computing the dot products only in a single cell, we can look at the neighboring cell and compute all of the dot products to check basically for robustness. Instead of having one, we're going to have multiple ones. And this already solves most of the problems. Not all of them, but most of them. Then what we did is, as you can see here, a bunch of the triangles are flipped, and there's still the problem of the remaining holes. So what we did is modifying the marching cubes traversal of the space, which is just marching cubes. You just take one after the other, all of the cells that you have. Here we want to change the order of traversal, and specifically we want it to be breadth first. In this way, we can follow the surface, mesh the parts that we are sure of, and leave the difficult ones for later. For example, there's a hole here and one there. They're not going to be meshed until we have the rest of the surface, so we have more information to get what was actually supposed to be there. And this makes it better. Again, not perfect, but better, especially for garments. Yeah.
This wouldn't matter for the original marching cubes, right?
No.
Just because you have this version of it that looks around a bit more.
Yeah.
Traverse order now.
Totally correct. Yes. Yeah. So in general, we got like better results compared to existing methods, in particular to ball pivoting, which is a super slow method, which gets good results, but it's super, super slow, like 1 hour compared to 1 second. And better results than inflation. Inflation means that we consider the garment to be an SDF, so to have a small volume, okay? And the volume depends on the resolution that we choose. So if we want the inflation to be fast, then we're not going to get a good approximation of the garment. It's going to be very thick. The slower it gets, the higher the resolution, the thinner the garment. And as you can see here, of course, the inflation approaches our method at a very high resolution, but our method gets basically consistently good results. So again, this is very good for garments, but it's not good, for every kind of shape. So this has a very garment-specific heuristic. So this is another work that we did. So how can we generalize this heuristic to be good for the most possible shapes as we can? And surprise, neural networks. So what if you use a neural network to define the heuristic that we need? So in this case, we define the problem as follows. We have our cell for marching cubes with the UDF values and the gradients that we computed. And we use a neural network to compute the pseudosigns. Okay, so these are pseudosigns that are just like the signs of an SDF, but only locally. They don't make sense globally because there is no inside or outside, but locally they make sense. And then we can use any SDF-based extraction method to get the surface in that cell. Okay, in this case, matching queues, but you can use other stuff. So the way this works is that we output. So how many possible configurations do we have as output? We have 8 vertices in a 3D cell. So there should be 2 to the power 8 outputs, but since it's a UDF and there's no inside or outside, there's a symmetry. So there's a total of 2 to the power 7. To make this work, we train the network with a cross entropy loss computed on watertight shapes. We need them to be watertight for training because we need a ground truth SDF to supervise that with. Okay. We normalize the input UDF values by the voxel size, which makes this resolution agnostic. It really doesn't care about the resolution. And then we inject the noise on the training set to make this work not only on perfect UDF, but especially on neural UDFs, which is the point of the whole thing. Okay. Is this kind of clear, the way it works? It's really straightforward. Yeah. No, but good point. So argmax, we use it only when we mesh. For training, we use a softmax. Yes. So these are a bunch of results. As you can see, for example, compared to mesh UDF, which was the previous one that I presented, the garments are basically the same. It doesn't change anything visually, at least. But the cars is way better. Okay. If you see here, I'm not sure if I can zoom in. Oops. Yeah. So you see there's a bunch of artifacts here, which is due to the fact that the heuristic of mesh UDF tries to follow the surface, you know, as if it was a garment, but it can't because it's a car that has a very different features, whereas our method doesn't. And the artifacts you see are mainly due to the resolution chosen. The higher the resolution, the less the artifacts. And these are, sorry, on noise-free UDF. Okay, so this is perfect, a real unsigned distance field. What happens if you use a real signed distance field, which again is what we are interested in? So again, we are better than the previous methods in this case, especially in these ones, but it's still kind of bad. That's the point. It's still kind of bad because, as I said, there's still a lot of work going on in the UDF representation. So it's very difficult to use neural networks to learn a UDF due to that non-differentiable part of the field. So again, this is a research, important research topic. But okay, given what we have, can we do better than this? And to do better than this is my latest work from this year that we submitted to NeurIPS. Okay, another result, sorry, forgot about this. So you see here, this is our method. This is mesh UDF. This is again our method paired with another one compared to the previous one. So for example, this one is missing the wheel, one part of the wheel. Here we recover it. And here again, we have way less artifacts than mesh UDF, same as before. So as I was saying, the problem with neural UDFs is that, okay, we are missing a bunch of details. They're difficult to get in an SDF. When you want to get a better surface, you mesh it at a higher resolution. Can we do the same with UDFs? So we have this at 128. Can we mesh it at 256? Okay, more details, but it got a bit worse, you see, like we lost a bit of the surface. Can we mesh it at 512? Not really. Not really. It gets way worse. And the reason why this happens, again, is this. So if you check what happens, this is a slice of a plane. So this is a true UDF. In white, you see the zero, the actual zero, or at least, you know, an epsilon. And here a neural UDF. And as you can see in this part, for example, it's not really reaching zero or a low enough value. So when you try to mesh it at a low resolution, you don't really care that much. You are away from that part and you get a surface there. It's not going to be detailed, but you get a surface. When you try to increase the detail, you mesh at a higher resolution, you lose the surface altogether. And that's a big problem. So in this case, this is again mesh UDF. This is our method from ECCV, so the previous one. And this is another method, dual mesh UDF. And okay, they have different problems, but the one problem they all have is that they're completely missing that part, that it was supposed to be there. So what we decided to do is that the approach we want to take is similar to what you do, for example, with transformers, that they regress on their own output. Okay, we can't really do it here because to do it here, we still need to define a traversal order to get new tokens and to progress the new output from the already computed tokens. But defining the order means that we define a heuristic, and we didn't want to. So what we did instead is we use a network to extract the pseudosigns of the whole surface, and then we input all of these pseudosigns back to the network, which is going to extract another layer of pseudosigns in a second iteration. And then we do it again, again, and again. This is a general idea. Of course, I'm skipping on some details, but this is the general idea. And this is the kind of behavior you get. So in the first iteration, I think you see it better on the plane, you get an initial surface like this. And then the more you keep iterating, the more of the rest you get. And the reason why this happens is because if we go back to the previous slide, here we do have information that there should be a surface there. But unless we know that there was a surface, in its vicinity, then we don't really know if we should mesh that part or not. Maybe there's a problem in the field. Was there really supposed to be a surface in the blue area? We only know if we mesh the white part. So that's the idea. Yeah.
So at a high level, what further iterations are trying to optimize is the fact that surfaces don't just disappear. Is that what the network knows and tries to get right?
Yeah, basically, yeah. So that's the idea, and these are the results. Okay, so that's the same chair as before, and these are the results with the new iterative approach. Okay, so you can increase the resolution, and you're going to get more detail, and you're going to keep most of the surface. Of course, it's not perfect. This is still an open field. And again, we have projects about this too. So if you're interested, we can. These are more results. As you can see, I got better at rendering meshes in the meantime. Nice. That's what 2 years of PhD do to you. So this is the iterative refinement, the latest one. And as you can see, it's the only one that is able to retrieve most of the surface. Again, not all of it, but most of it. Yeah, okay. Any questions? Okay, so what time is it? Okay, maybe I should quit then. You keep going. No, I'll just very briefly talk about neural radiance fields, just to introduce Sakib's work. So a neural radiance field, which again you might have heard of, is just a coordinate network that enables you to do this. Okay, this is a multi-view reconstruction of something. You get a bunch of images of an object or of a scene, and then what you want to do is render another view. For example, from the top or from the bottom or from in between a view that you already had. Okay, this is the general task. And the way you do it in NERF is by having this F, which is a coordinate network that has as input 5 coordinates, x, y, z, of a point in space, and theta and phi, which represents the viewing direction. Okay, because of course the output image that you want out of this depends on the viewing direction. And the way it works is that given a specific point of view, you render from that point of view, you need to render from that point of view the scene or the object or whatever you have. To do that, you process the whole thing exactly as if it was a real camera. In a real camera, you have a lens, you have a sensor, and you have the camera center, okay, that basically projects all the rays to and from reality, okay, and you get the image to the sensor. So here you do the same thing. You have a center, and you project rays from the center to the pixels. You define a number of pixels that you want in your virtual sensor. And these rays that you shoot through the pixels are going to intersect some space, okay? And this space is defined by the network. So from each direction and for each pixel, you query the network to get what you need, okay? And it's been proven in the original NERF paper that the way to do this effectively is, instead of having one single query per ray, is that you you basically march on the ray. It's called ray marching. So you shoot a ray on a pixel, and then you query the space in multiple locations, okay, to estimate an integral. The integral that you need to estimate is this one, okay? Doesn't really matter too much what it means right now, but the point is, this whole thing is an integral estimation, and the output of the network is not only the RGB color of that point in space, but also a density sigma, okay? That density sigma is going to tell you where the object is. Ideally, it's going to be 1 where the object is and 0 where it isn't, but of course, it's a neural network, so it's not going to be like that. And that's why you need this whole integration. So if you, let's say, ray 1, in the x-axis, you have, you travel further along the rays. On the y-axis, you have the sigma. At some point, you're going to encounter an object here, and the sigma is going to increase, okay? And then it's going to decrease again. So when you estimate the integral, you keep querying the ray along the specific direction that you needed. You get those values. Once you reach the higher the density of that value, the higher the contribution to the integral. And so this is exactly what is written here. So the sigma only depends from the viewing direction. Sorry, that only depends on the location in space. RT is the location in space. And C, the color, that depends both on the location in space and the viewing direction. Because of course, a color can be slightly different in different directions because of lighting and other stuff. This big T value is this other integral, which simply says that the more density you encounter along the ray, the less important the next points will be, because your view is going to be occluded at some point. After you encounter the object, the rest is going to be occluded. So you don't care about the rest anymore. So this is exactly what it says. It's basically a smooth rendering of what you have in reality, in which you cross an object and that's it. Okay, this is a smooth version of it. And it's by ray marching, you estimate the smooth integral. Okay, sorry. Compared to some other previous methods. And as you can see, it's quite accurate. Like you get really, really cool results. And this was the very first NeRF work. In the meantime, there has been like thousands of them, and they got better, faster, and cooler in every sense, basically. I think this only compares the same scene for everything. Okay, no, there's another one. Yeah. You do see a bunch of artifacts. Again, it's not perfect, but it has gotten better. And yeah, I mean, it was a breakthrough when it came out. It was a huge breakthrough because it was just impossible to do this in a good way before this. The problem with NeRF is that even though there has been improvements, it's still a bit slow. And another method came out that can do this whole thing better. And I guess Sakib is going to talk about it.
So hi, everyone. I'm going to talk about, as Federico just mentioned, about some explicit methods instead of like implicit representations, which is all neural networks. So maybe we can like focus less on that now. And meantime, it will be also more focused on real time, like, I mean, to do it faster. As Federico also mentioned, like NeRFs are quite slow because you have to do this ray marching, which is like you're trying to like figure out the output at each point, which is very costly. Before we move, like, yeah, something about me. I'm also working in CVLab, coming from Pakistan. Like, that's my city where I grew up. And I did my bachelor's there, coming to TU Munich, did my master's there, and had an opportunity to work at ETH as well with Luca Benini, which was my prime focus, which is still my prime focus of my PhD. It's mostly around like model compression, neural network compression. And now I'm doing a PhD about that. Along the way, like I did many internships, and currently I'm also like doing one at LauzHack just across the road. So yeah, before we move towards like explicit representation, I just want to emphasize a bit more on like why are we so interested in doing 3D reconstruction from 2D images. One of the big thing, like for example, as we see the internet, like, I mean, there are a lot of generative models now, like you doing like LLMs or even image generation as well. But when it comes to 3D content, like it's very less, like, I mean, because one of the main bottleneck is you do not have much more data. If we like scale it up a bit, you can see a very tiny point as compared to images or text-based data that is available on the internet. And that makes 3D generation like quite challenging. And what we want to do in this case is we want to take all the image data possible on internet and try to reconstruct scenes. For example, in this particular case, everybody has taken a bunch of images of Colosseum, like in Rome, where Federico comes from. And but in this case, like the exact 3D model of this particular architecture, like it's not available. So we want to exploit this 2D data to reconstruct this. why do we want to do this is if we have like more understanding of 3D content in our surrounding, there is a huge potential for like robotic applications, or like, for example, another thing that is immersive broadcasting. Suppose like you are sitting or watching a football game and you want to really have like first person view, want to move inside the ground, like change your seat, you can watch it from any angle possible. And this is where like it's same thing that is happening here. You have bunch of images and then you try to reconstruct how the scene will look like in 3D. And once you have that, like you can put yourself in there as well. That's what like interactive telepresence will do in future. And I think a bunch of companies, and even what I think Federico is going to work about is telepresence at Meta as well. They are quite focused in this regard, and sort of I'm working in the same direction as well at LauzHack. So coming back to Nerf, so this is like the same slide as what Federico showed, like, and I just want to again emphasize, like you have this frame arching, like, and you are like trying to measure output at each point, which is very costly, and the rendering, as Federico mentioned as well. So now we come towards explicit representation, which is points basically in 3D. And in this particular case, let's suppose like you have a few images of this room taken from like different angles, but you know like precise location of camera. Like for example, one was taken from here, like exactly like the coordinates in 3D. And you feed this image like to structure. I don't know like if some of you guys are familiar with computer vision like course here at EPFL. So basically structure for motion, what it is doing is, let's suppose you have a bunch of images taken from different points. It is trying to compare like which 2 points in each image are same, like so that where they are intersecting in 3D basically, because you know the positions of camera as well in this particular case, what we are doing right now. And this is like sparse initialization, where you have like bunch of 3D points, you know, like, okay, there exists something at this particular point in our scene. This is what you initialize with. And each of these points, these are basically like Gaussians. You can see it as like 3D representation. And all of these have like some parameters which are learnable, similar to sort of neural networks. And you have like mean, like where exactly is the point located, like the covariance matrix for the scale and everything. Color, like what exactly, like it in RGB values or like spherical harmonics. Like, I mean, the first paper that came out was using spherical harmonics, but which was very costly to store. So people went a bit towards RGB storage coloring, like where they can reduce the capacity. And opacity as well, like how opaque it is, like how dense it is. What Federico was also mentioning about like the transmittance. So this defines that. So yeah. And apart from that, like you make it, the main contribution of this paper, like splatting existed before as well. They made it differentiable. Like, I mean, the whole scene, like you just give the views and like all the Gaussians will be trained, like you will know where exactly these points exist in 3D. And then the densification process, because we initialize with very sparse, like a few Gaussians. And then how does this happen is like, for example, in this case, you have some sort of under reconstruction. For example, a very small Gaussian is representing some surface. So what you are doing is like you add another Gaussian next to it so that it can represent the whole shape better. And if you are doing over reconstruction, that means like your Gaussian is much bigger than what it is supposed to be. You can just split and make it to represent the shape better. The loss is like just mean square error, and like with some structure similarity between the rendered views from different angles. And in this particular case, how we are, the data set, like, or in this case is like pixels. You can see it as, it's not like images, because you have a bunch of images of the same scene. It's not like classification where you have a lot of images and you are trying to classify what exactly exists in this one or that one. You are trying to, in this particular case, learn pixel values. So each pixel is a data set. You can see it as that. And for the test rendering views, like you keep some views where you are not, where you do testing how good your scene reconstruction is. So yeah, that pretty much sums up like how your explicit point-based like reconstruction is happening, which is recent method, and the benefit was like so alongside the computation benefit, there is another one, because so you know like which Gaussians are representing the tree in this case, and also or the background. So scene editing is very much like important as well in 3D scenes, and which is not possible in case of NERF. For example, if you are storing implicitly, like you do not know like how to change your or manipulate your network to change, for example, the color of tree. But in this, oh my God. But I just want to show, like, I mean, the scene editing, like, for example, I just want to change the colors of color of the leaves. It's very much simpler as compared to NERF as well. This is why, like, a lot of apps, for example, Adobe, like, they are also working a lot with Gaussian splatting now. And another one, like, of course, which Federico also mentioned, like, NERF was very slow. But important thing was, like, NERF was not as big as Gaussian splatting. So if we compare, like, the storage, 3D Gaussian like points which are explicit, you have to store them somehow, and like that makes it it requires a lot of storage, but it is very fast. And this is the time axis, like how things are progressing. And in this regard, a lot of work has been proposed, like to compress and make for example, like compress this Gaussian splatting representation. And for example, pruning has been proposed. For example, if you have a lot of Gaussian points, let's say like of many colors, you try to identify which one of them are super important to preserve like the rendering quality, and you throw most of the others like which are not that important. Like for example, you might have a negligible effect on the quality of the output. And also like quantization, people are creating like code books. For example, in this case, like you see like 3 colors which are orange, reddish, they are quite similar to each other. You just store as one. And this is one way of compression. And then like there is like Huffman or like zip compression, like just to store after it has been rendered. This happened like maybe in 2024, right after the 3DGS paper came out. But it was mostly targeted on static scene. And one big difference between static and dynamic scenes is like, for example, in this case, you can see nothing is moving in the scene, it's all static, but it's like only the camera is moving. But when it comes to dynamic scenes, you can imagine like the person is moving. It's hard to find out which points in 3D are important for future frames. For example, in this case, like in this particular case, okay. Yeah, I just wanted to mention, like, for example, the background where the guy is standing, it's not that important, but like when you are training your 3DGS, you do not know what subsequent frames will bring. Maybe the background might change, so you might need to store those Gaussians or have more importance to that as well. But in this case, it is not changing though. So the guy is, the Gaussians which are representing the guy, they are more important. So yeah, yeah.
Maybe I missed this part, but do you understand correctly? So in this whole Gaussian thing, we have like a view of our scene from different cameras, and then for each point in the scene, we create each small Gaussian, and then we try to estimate its parameter.
So the Gaussians are being trained for every training view that is possible.
So Gaussians are in 2D, they're not.
They are in 3D.
Not placed inside 3D scene.
They are in 3D. Actually, these are 3D Gaussians, but they are. This is like something like, for example, you can imagine they are in 3D space and they are splattered onto the images, and then you have rendered view, and you try to compare with like the images that you are feeding to train your 3D scene, like how good you have rendered it versus what you had as ground truth.
Also, each Gaussian has its own coordinate.
Yes.
In 3D,
yes.
And we just split our scene in like some grid of points, where for each point we create its own Gaussian. Or how do we understand how many Gaussians we need for this scene?
So this is where densification thing comes in. Like, what we want the best rendered quality that is as good as like the ground truth. And these are the, for example, you can imagine there are like image planes here, like in front of the camera, and you are seeing it from 10 different views. and you're trying to optimize where exactly my Gaussian should be in 3D so that it looks good in both 2D images. And this is how it is getting trained. And if you think like your quality is not good, you densify more, you add more Gaussians, you need more points to represent that 3D scene. And that's what makes it better after like a while.
So it's not only like 5 points, 5 parameters that is.
Yes, it's not only this, there is like you add more Gaussians, and also like every Gaussian has these parameters.
And also coordinates.
Yeah, the mean is basically representing the coordinate. Yes. Is it clear? Yeah.
For rendering a view, we need to sample from these options.
For prevent, yeah, I mean, yeah, exactly. Like not like to sample, but it's just like you can see it like you just change the camera, like where you are looking from. Your points already exist in 3D. Your camera is just moving a bit like to a novel view. Huh?
We sample basically 3D shape.
You splat them onto a 2D plane, which is the image basically. That's why there is this word like splatting, because they considered each of these Gaussian as a splat. And
so this splat is a 2D Gaussian?
Yes.
But we still have to sample from that. To render the view.
Maybe I'm confused. Like, I mean, maybe I'm not understanding your question. So you can view it as like you have a 3D body, like 3D blob in 3D space, and you have a image plane in front of it, and it is getting like splatted on this image plane, and you are looking this image.
Because Gaussian thing is like a random variable. It's like does Gaussian means like a Gaussian distribution, like
No. No, it's just like you can see that it's a shape. It's a shape. It's not a distribution. Like, I mean, as in like, yeah.
So it's cloud of points rather than a distribution. So what's the point in saying use Gaussian?
You can view it as like just it's not a sphere. It's so that like your shape doesn't say spherical.
It's an ellipsoid.
Ellipsoid. These are basically 3D ellipsoids.
Does it have a clear boundary?
This is why like it starts to fade like slowly. I don't know. Like, I mean, maybe I should have shown like
They are ellipsoids, but they're Gaussian, so there's no clear boundary. Like
they fade in space like as much as you go away from the center.
To render them, we need to sample or no? How can we? Because we need to sample or like make a isosurface of like
you consider them like, you know how you rasterize? You know what's rasterization rendering? No. So in rasterization, let's say you have a mesh, a bunch of triangles. You slap them on the camera sensor. Okay. So if a triangle is in the scene and you're looking at the scene from a specific direction, then you can take the triangle and just project it on the camera sensor. That's what you do here. You take each Gaussian and you just project it to the camera sensor.
Does this sort of make sense now? Yeah. So this is like having your 3D like Gaussian, and you're just like mapping them onto an image space.
Okay, so it's like for each coordinate on the 2D plane, I would take like the probability in this Gaussian as a weighing of the order of that distribution.
I think so. The way like in the intersections is weighted by probability.
Yes, it's the same formula which they were using for NERF, like to get the final color, like what it should look like in this pixel. It's exactly the same. That's why I think I should have shown this. I have hidden this slide, but it's on the ray, like you are trying to, and you can see it as the same alpha compositing. That's what they call like the transmitters thing. They're using exactly same here as well. Okay. So yeah, with dynamic scene, like it's very difficult to identify, like for example, which Gaussian is important, like for the future frames that are coming. And if we try to plot like just importance for each, this is for a dynamic scene. And on y-axis, you have like different Gaussians. And for each one of them, you can see it's very fuzzy. Like, I mean, in one frame, it is important. In the next time frame, it's not important. So this is what we don't want to see. If we want to like get rid of some of the Gaussians to reduce the storage or like the increase the rendering speed. We want to have more regularized thing, like where you can say like in first frame that this Gaussian was not important and it should stay not important in the whole scene. And this was not explored like until last year November, like when I worked on this. And I will show like what I did afterwards. But for example, for dynamic 3D GS, there is you can see it as like you have added a time dimension to it. For example, before that it was a static scene where you have like bunch of images, and now like you have time dimension where like your frames are being captured at a different time. So the scene, the people are also moving in it. For example, see it like this, like for example, where people are sitting here right now, and you try to capture this scene. There will be some movement in the scene as well after each time frame. And there were like two main types of methods for these dynamic scenes. And one is deformation based, where you learn like the first frame, like how it is from different angles, similar to 3D GS. And for the next frames that are coming, you just try to predict like where each Gaussians will move in future, like, and also their rotation and scaling metrics using an MLP. But of course, the downside is you already know the whole sequence. So you know what the next frame will look like if you have to train the network. And also for 4D primitive, where you add another time dimension, you basically make the opacity and the trajectory a function of time, where you just like give, okay, this is the Gaussian, and like at this time, where exactly it should be. So it's just predicting XYZ and also the rotation and opacity metrics. Both of these types of method, like the downside of them is that you need to know the whole sequence before, and which is not what we want. We want something that can render things on fly and also don't know what is coming, still try to preserve the important Gaussians. And also another limitation for the state-of-the-art methods, they do not have a lot of motion. For example, as I mentioned before, if you see in this particular case, most of the background is static. And this is the, on the right side, you can see how many Gaussians are moving. It's most of them are just static, and this is the frequency. And also they see the whole sequence. And we plotted like some of these state-of-the-art methods. If there is a fast motion, for example, people throwing basketball, they fail completely because they are trying to guess this movement or like measure or calculate this movement through a polynomial, third degree, or like using a small neural network, which fails to predict the right coordinates for each Gaussian. Yeah.
Yeah, so I have a question regarding the representation for dynamic Gaussian slicing. Do they store spherical harmonics, or they represent the scene without that? Because you said that Gaussians should rotate during the movement, and they have to change the spherical harmonics because of the Gaussian rotation and X, Y.
So yeah, initial method, as I mentioned, like it was using spherical harmonics, and more like we are like progressing in recent times, people are not using them anymore. So just to store, like, I mean, these things, you need a lot of parameters. And to have like more real-time thing, like you need to reduce parameters, and people have like realized over time that it is not as important as it seems to store all these spherical harmonics. You can do it with less degree as well, maybe like 1 or 2, it's enough.
Yeah, but still they do store.
Yes, but it could be like it's just 1-2 degree, but initial paper had 13.
Yeah, and but during
13 parameters, sorry.
But during the optimization, they have to rotate those parameters. I mean, they have to change then because the Gaussian is rotated.
Why do they have to change? I didn't get it.
Yeah, so
Yes. So you do not need to rotate, sorry. But maybe we can talk it later, like if you have any concern, maybe. Yeah. So yeah, it fails. And this particular method that was also from the same authors as the original 3D GS, they were doing like deformation-based network, but where they were explicitly learning the positions and rotation and scale for subsequent frame as well, instead of like deploying some neural network or like seeing the whole sequence. It was frame by frame, and also they were storing it explicitly. So this is the reason why they had like a very good rendering view, like if you compare it to ground truth versus like some of the state-of-the-art method, which were lightweight. But the downside, of course, was like because you have to store all these parameters, so it was space inefficient. So we try to compress this and try to regularize, as I mentioned before, and with our method, like which was temporally compressed 3D Gaussian splatting, we try to regularize as much as possible so that importance of each Gaussian incoming frame also stay as low as possible. So basically, like we try to we train the first frame and then like add some like regularization loss, so that like Gaussians which were not important in the first scene, they should stay not important in the subsequent frames as well. And the other Gaussians should try to like somehow make up for the loss that they have to bear. This was one thing that we did, and based on this we pruned not important, and we could like reduce up to like 67 times storage required. And then another thing was like vector quantization. As I mentioned before, there was a lot of work around code books. So people were creating code books for different Gaussians and then store that only. But in this case, we used mixed precision quantization for each parameter. We were like giving a flexibility based on some gradient loss that, for example, color is very important in scene reconstruction. So we will give higher precision to that. Instead, like for example, scale is not as important as color. So maybe that can be stored in 4-bit only. You do not need 8 or 9-bit, which was given to colors. And the last one, like, of course, people were using this zip compression or Huffman compression just to store these sparse metrics. What we did was like key point interpolation. For example, there could be a Gaussian which is not moving at all as a background. For example, it stays static throughout 150 or 300 frames that you are capturing. So you do not need to store all these values for each frame. Instead, you can just store like 2 or 3, like for example, for 0 frame and 150th, and you can just interpolate, it stays static. So you do not need to store the position for each frame. So our results were like quite good, like even with 67 times compression, like you can see, like, I mean, we reconstructed as good as dynamic 3D GS, the original method. And yeah, this paper is also under submission. One of the key limitation to this, and for the future research direction as well, if there is a new object coming into scene, for example, let's suppose like we have reconstructed this scene right now here, and somebody comes from outside, which was never seen in past 150 frames. How would you represent that person? Because there are limited Gaussians. Gaussians are not increasing, they are just moving now in the scene. So in this particular case, like it's the mobile phone. Like for example, this guy like takes out the mobile phone and you can see it's not represented very well. And this is a new object. And this is one of the key bottleneck in 3D or dynamic 3D GS scene reconstruction. Yeah.
So Gaussians, they try to approximate the object in a scene, not like the color in the scene. Because if it was the color, they could maybe Gaussian could just change the color and send us this.
So there are a few things, like, I mean, of course, it's a bit more complicated than that. In this particular case, we are fixing Gaussians for each object. We do not want to just, for example, a Gaussian that is representing this person should stay like with the same sort of color or like same coordinates. It should not move, like, for example, in that corner. And this is why it is very difficult to represent a new object, because we want to in future track objects as well. Just imagine if you know the 3D points which are representing a human. If this person is moving in space, you already know the position of that person. Now you do not need to estimate it again. So this is why we want to like associate some Gaussians to each object from the very beginning. And then we just move those like wherever the guy is moving or like the object is moving. So this is why it is a bit challenging, like when there is a new object, because we want to densify only for the new object, not for like something that is moving. It's clear? Yeah, I mean, like there is a student working on this, and if you are like interested, there is potential in that direction as well. Right now, like what I am working on at LauzHack, it's also one of the potential application. This is related to 3D video conferencing. Since many years now, we have been stuck with these boxes where like a lot of communication is lost during interaction. And we want to make it a bit more immersive. Like maybe some of you have heard about Google Starlink project or Google Beam, that is now, it's called that now. And this is what they were doing. They have like, bunch of cameras installed on a screen, and they try to like feed different images to your left and right eye and give you a sort of perception of 3D or like depth, basically. Like you feel like people are like right in front of you, not exactly in a screen, like for example in Zoom. There's a lot of work going on in that direction. Actually, LauzHack also has some of these screens. If you ever want to try, like feel free, you're welcome. It's very cool, actually. I was very impressed when I saw it for the first time. It looks very real. And in a world of AI, like for example, there is this thing, for example, from 2D video streams. For example, if I'm talking to, let's suppose, Federico, he can like feel like he's right in front of me rather than like, in a screen stuck there. And this is what they are trying to work with. For example, in future, I think 3D video conferencing will look more immersive, where you will feel like you are talking to a person in presence, for example. Right now, like there are diffusion or GAN-based methods that are being used, but we want to deploy this on small webcams, which is a bit challenging because these are very big and huge models. And this is why like I'm working on a bit of compression there as well, so that we can try to work. Of course, it's a far-fetched idea, in my opinion. Like it will be done maybe in like 1 or 2 years, not right now. Meta is working a lot on that telepresence like thing, and I think it's gonna be very cool. So yeah, this is another thing. For example, let's suppose you have a feed coming in and you want to view it from different directions. You are having a 3D video conference in a room. You feel like you want to move inside this, like look it from a different angle. You want to sit somewhere else. This is gonna be that. And another like good direction, which bring back again to shape reconstruction, surface reconstruction, is when 3D Gaussian splatting came out, there was another method which was fuzzy metaballs that also came out, didn't get as popular as Gaussian splatting. One of the big thing was like it's the rendering is slow, and also it's a bit different. It's not exactly as Gaussian parameters and everything. Some representation is a bit different from that. And but the cool thing about this is like they are doing the surface reconstruction, which is far more important in my opinion than just having some points, because if you have shapes, you can understand things much better in a scene. I think Chen might talk about it as well. And one of the, I think, futuristic direction, or like I think important direction as well, is on the fly scene reconstruction. You do not want to see the whole sequence before reconstructing it. You want to see it frame by frame and try to have 3D of that. This is more practical because that's how we communicate, and that's how the images are, let's suppose, coming back to the same example of broadcasting a football match, you are seeing it frame by frame. You do not know what is going to happen in future, so you want to have methods which are like streaming it online. And another one is with uncalibrated cameras, whole 3DGS domain uses calibrated cameras. So basically, the position, the pose of each camera, where exactly it is in 3D space. And there is a lot of research right now going on in using uncalibrated cameras and trying to reconstruct the whole 3D screen from that. This is way more practical, as I mentioned before as well. If we want to reconstruct this whole scene, we just need a bunch of images. We don't need to know exact precise location of each camera. And then another one is like you give an image, for example, in this case, small like teddy bear. I think it's not gonna play.
Yeah.
So yeah, basically in this case, you just feed this image to a video diffusion model, and it creates a video of that using 3D scene. First, it generates a 3D scene from just one image using diffusion. What you are doing is you take one image, create like other views using a diffusion model where you can do image generation, and then using those multi-views, you create a 3D scene where you can move freely. So this is why like the camera is a bit free, like you can move around. The last one, like, I mean, I think this is gonna be more important for coming times. It's generating videos which have like plausible geometry. You might have heard of Sora and like VEO2, which is becoming right now very popular. And there was like one method that tries to, you can say, benchmark like video generation models, which one are better. And you can see here, like if you do 3D scene reconstruction of Sora, using the videos from that, actually it is much better than the other one. And this is why like Sora is making much better videos as compared to others. So this is one of the ways how you can test like how good is your video generation model. Actually, I was a bit surprised there is not a lot of work coming in this direction, but I think this is important for future world models where you need to interact with the environment. You need to have more understanding what exactly is in front of you rather than just a 2D image plane. So yeah, that's it. Thank you. And if you have any question, I was not very well prepared for this. Like, feel free to ask later. And yeah, thank you.
Okay. I'm sorry I cannot join in person because I have some personal issues, and I guess we are a bit over time. So I'll just go through my research very quickly. So actually, Federico and Sakib already introduced about like 3D representation and 3D reconstruction. So I'll just start with 3D interaction. For 3D interaction, the goal is to, like how we interact with the 3D physical world. And in this direction, actually, there are many different tasks. And for me, I've been working on object pose estimation. It's very important in 3D interaction, and it's also very important in some like real applications like robotic manipulation and augmented reality, because it can provide a detailed 3D understanding for the object. And then you can see, showing this demo, the robotic arm can know how to like grab the object. And this is a basic setting for object pose estimation. We have a RGB image, and then we have a 3D object model, and the goal is to predict the 3D rotation and the 3D translation of the object. And actually, we have a real application along this direction, as you can see here. Nowadays, actually, we have like more than 34,000 debris in Earth's orbit, and all of this red dots are the debris, and the other white dots are our satellites. And the existence of this debris is actually a growing risk of collision with our satellites. So we have a project aiming to clear the debris in space, and this is a demo how we are gonna do this. We plan to launch a satellite with a robotic arm, and then we're gonna use our algorithm to detect and compute the 60 pose of this debris, and then we can grab the debris and maybe take it back to Earth. And this is a demo of it. But unfortunately, we cannot really use the most. We cannot really use the existing methods because they only work at an instance level. So the first question is, what is an instance level object pose estimation? So basically, as I'm showing here, we have a bunch of objects, and then we train our method, let's say on these 4 objects. And during testing, we also have exactly the same objects, but in different poses, meaning that we can only compute the pose for these 4 objects. But in real applications, there might be some new objects which are not included in the training set. And for these new objects, the appearances and the shapes could be very different from those of the training objects. So that's why these methods cannot really generalize without retraining on these new objects. And here I have a detailed example showing why like the the deep learning method cannot really generalize to new objects. For example, we have a binary classification network. We want to train this network to classify an image to a cat or a dog. And then to train this network, we have a set of images. We have like a bunch of images detect cats. We have another category of the dog, and then we can use this training images to train this binary classification network. And then, of course, during testing, if we have a dog image, we can use this binary classification network to predict the label of this object. Of course, it's going to be a dog. But if we have a rabbit, if we still use this binary classification network, of course, we cannot get the correct label because none of the cat or the dog is correct for this image. So that's why it's really hard to make a deep learning network generalizable to unseen objects. And this is actually our goal. We want to achieve a generalizable object post-estimation, meaning that we first train a network on, let's say, a number of objects, and then we can directly run inference on any objects without any retraining or fine-tuning, and then it can open up some new possibilities and real applications like robotic manipulation and augmented reality. And next, I want to mention the importance of reference, because as I already introduced, it's not that easy to achieve the generalizable object post-estimation. And to achieve that, we need a kind of like reference. So first, given a query image, it may contain lots of different objects, and we'll assume all of these objects are unseen objects. In this case, without a reference image, actually we don't know like which object we want to target on. We don't know which object we want to compute the pose for, right? So that's why we need the reference to first identify the object we want, and then we can compute the pose for this object. And secondly, actually for post-estimation, if we don't have a reference for the unseen object, the post-estimation is actually an yield post problem. And here, actually, you need some knowledge about multivariate geometry, because the actual pose we estimate is a relative transformation from the current camera frame to a predefined object frame. And if we have access to the 3D object model, of course, we can define this canonical frame. Otherwise, as you can see here, there could be multiple possible object frames. And then in this case, of course, we cannot get a meaningful relative transformation. So that's why we need the reference to first define a canonical frame, then we can make the post-estimation meaningful. And also for the reference, to define the reference, there are lots of different settings. And next, I'm going to introduce them one by one. So the first setting is dense reference images. So in this case, we assume that we have dense view images as reference. And these images could be synthetic if we have access to a 3D object model, because if we have a 3D object model, we can do image rendering along different viewpoints to get lots of synthetic reference images. And in another case, we may also have like real reference images. Let's say we have an object here, and then we take lots of real images around, like from different viewpoints of this object as the reference images. But anyway, once we have this dense view images as reference, given a query image that contains this unseen object, we can run an object pose estimation algorithm to get the object pose. And also, along this direction, I have some works, but I'm not gonna introduce them in details. So briefly speaking, for the first one, the goal is to estimate the 3D rotation of this unseen object. And for the second one, the goal is to localize this unseen object in the RGB image. And these are some demos. You can see for this one, actually, we never train our method on this satellite. We just directly run inference on this unseen object, but you can see our method can precisely get the 3D rotation of this unseen object. And also for this object, our localization algorithm can also robustly localize this unseen object from different viewpoints, and also with some zoom in and zoom out process. Okay, so for the second setting, sometimes we may not have access to dense view images as reference. We may only have like sparse views. For example, here we assume that we only have 5 images by default. So given this 5 images, we can run a 3D reconstruction algorithm like structural motion. And in this case, because we don't have dense view images, the reconstructed quality could be really bad, like this. But in this case, we don't really need a high quality reconstructed 3D model. We only need a 3D bounding box like this. This is what we need. We have a 3D bounding box. And after that, we project the 8 corners of this 3D bounding box to the reference images. And then we have a bunch of, projected maps. Like we have, for each image, we have 8 2D corners from this 3D bounding box, right? And after that, we have a transformer network that will learn like a transformation from the reference to the query. And the actual output we have is the 8 corners on the query image. And given this 8 corner, the 8 2D corners on the query, and also the 8 3D corners, we can run a PMP algorithm that actually gives us the object pose for this query image. And here I also have some demos. You can see for all of these unseen objects, our method is able to robustly get the object poses. And also in some cases, you can see, for example, this one and this one, there is occlusion because of the hand. And in this case, we can still robustly get the object pose, meaning that our method is quite robust to the occlusion. Okay, so the last setting is single reference image. So this is the most challenging scenario. So in this case, we don't have dense view images, we don't have sparse view images. What we have is just a single view image like this. And in this case, actually, if we only have this reference image, like a single view reference image, what we have is just a relative transformation from the reference view to the query view. We cannot really get the absolute pose for this query image. But if the reference is calibrated, meaning that we know the absolute pose for this reference image, we can derive the absolute pose for the query. Otherwise, we only have the relative pose in this case. And to compute the relative pose, a straightforward way is to run the image matching algorithms, and then we have some 2D to 2D correspondences, and based on this 2D to 2D correspondences, we can compute the relative transformation. And you can see here, if the viewpoint change between these 2 images is relatively small, we can get pretty good correspondences, meaning that we can get pretty accurate relative object pose. But if the viewpoint change between these 2 images is quite large, like this 2 image pairs, we cannot really get reliable correspondences. It means we cannot really run the image matching algorithms in this scenario. So we wanna, because of those issues, we wanna introduce some alternatives, and I have some papers, but I'll be focusing on the most recent one. So in this paper, first we don't assume any object prior, meaning that the first step is to somehow find the unseen object in this image. Let's say we have a current image, and this image includes lots of objects. And given this reference image, we want to first detect this image in the query image. So to achieve that, we have a multimodal open set object detection algorithm. So first, I generate some text prompt based on the reference image we have. For example, here I use pink toy cat as the prompt. And after that, I feed the prompt with the query to an open vocabulary object detector that gives us some object proposals. But you can see here, the resulting proposals are actually quite noisy. There are lots of incorrect bounding boxes, meaning that we still need an algorithm to somehow find the correct bounding box we need from all of these proposals. So that's why we have a second stage. So in this module, we feed all of these object proposals with the reference image to a feature encoder network. And after that, we have, for each image, we have a vector, which is actually a global descriptor of this image. And the following part is quite simple. We just compute the cosine similarity between two global descriptors, and after that we can just find the bounding box with the highest score as the one we expect. And also, as you may notice, for each proposal there's a score. So this score is directly predicted by this open vocabulary object detector, but unfortunately it's not really reliable. But I'm not sure if you can see the score clearly. For example, for this image, some of the scores of the wrong object proposals are actually larger than the correct proposal. So that's why we cannot really rely on these scores. But you can see here, our second after our second stage, the selected object, the bounding box is quite robust. And also, as I mentioned here, we cannot really rely on 2D correspondences to get the object pose, and there are lots of different lots of regions. Here I'm only showing one of those regions because first it's very complicated to get the object pose from 2D correspondences, because this is a pipeline. We have images, we have 2D correspondences, and based on 2D correspondences, we compute an essential matrix. And based on the essential matrix, we recover the pose parameters. You can see here, it's not, the whole estimation is not fully differentiable because of this, from essential matrix to pose parameters. This part is not differentiable. So that's why the whole pipeline is not fully differentiable. But by contrast, if we compute the pose from 3D correspondences, the whole pipeline is very simple. We just have 3D correspondences, and we can directly solve this problem to get the camera parameters. Of course, it's fully differentiable. But the main challenge here is how we get the 3D correspondences from 2D images, right? So to achieve that, we first introduce an autoencoder network. And briefly speaking, we have two images, one query image and one reference image. We have an encoder network. We lift the 2D feature map to 3D, and here we use a 3D volume as the 3D representation. So we just, for each RGB image, we encode the feature to a 3D volume. And of course, because we have two images, so that's why here we have two 3D volumes. And after this encoding part, we have a decoding process, because we want to make each 3D volume aware of the object information. So that's why we decode the 3D feature back to 2D and predict the RGB object image and also a 2D binary mask for this object. And once the training is done, for each image, we have a 3D volume as the 3D representation, right? And the next part is quite simple. It's quite familiar with point cloud registration, and the goal is to somehow align the 3D voxels in these two 3D volumes. And here we have some algorithms, which I'm not gonna introduce them in detail, but in general, we just want to make the whole pipeline fully differentiable. So that's why in this case, we can directly use the ground truth object pose information to supervise the training of this matching module and also the training of this autoencoder. Yeah, and here I also have some results. Here I am showing the absolute pose for the query, which are actually derived from the relative pose we compute using our algorithm. Yeah, that's it. I'm sorry I skipped lots of details because of the time limitation. And also, if you have any questions, please feel free to reach out.